So we're going to look at this division algorithm again for polynomials, and we're going to prove one little piece of it. So what we're going to prove is this uniqueness of these polynomials. So we're going to prove that Q and R are unique. Okay, and we're going to do that by supposing that we have two different versions of Q and R. So we're going to say suppose f of x is equal to q of x times g of x plus r of x. And we have that condition on r, so where the degree of r is greater than or equal to 0 and less than the degree of g, or r is the zero polynomial. And at the same time, we're going to suppose that f of x is q prime of x times g of x plus r prime of x, where again the degree of r prime is greater than or equal to 0 and less than the degree of g, or r prime is the zero polynomial. All right, so what we want to show here now is that q equals q prime and r equals r prime, because that would let us know there isn't a second way to do this. If you tried to write it a second way, it actually was the same as it was. It was actually just q and r over again. All right, so our goal is to show that q equals q prime and r equals r prime. So what we have now is that f was written two different ways, so I'm going to set those two different ways equal to each other because they both equal x. So I have that q times g, and I'm dropping the function notation just to make our lives a little bit easier. So q of x times g of x plus r of x is equal to q prime of x times g of x plus r prime of x. And rearranging that, I notice that I have g in common on the left and the right, so I'm going to move them together. I'm going to subtract q prime g from both sides and then factor, so that I get q minus q prime times g, and on the right, my r prime minus r. All right, so what we're going to do now is take that equation and try to find somehow something that tells us that q minus q prime has to be 0. So let's think about the left-hand side. We're going to think about the degree of the left-hand side. So if q minus q prime is not the 0 polynomial, then the degree q minus q prime times g is equal to the degree of q minus q prime plus the degree of g. Remember, in the setup to our theorem, g was not allowed to be the 0 polynomial. And so we know that this addition property of degrees holds like this. And we know that the degree of q minus q prime is at least 0. And so this whole thing is greater than or equal to the degree of g, no matter what. All right, so if q minus q prime is 0, we also know r prime minus r would not be 0 because the left-hand side is not the 0 polynomial, so the right-hand side can't be the 0 polynomial. And we know that the degree of r prime is less than the degree of g, and the degree of r is less than the degree of g. So the degree of r prime minus r is definitely less than the degree of g, which contradicts the degree of the left-hand side being greater or equal to g. All right, so on the left-hand side of that equation, q minus q prime times g, the degree was equal to g. On the right-hand side, the degree had to be less than g. And so we have a problem there. What we go back to then is say all of this, with this argument we were just making, was if q minus q prime is not 0. And so that means what we can conclude is that thus q minus q prime is 0, so q of x is equal to q prime of x. This also means that r prime minus r is 0, so r prime of x has to equal r of x. And therefore, q of x and r of x are unique. All right, so that's one little piece of the proof of the division algorithm.